Welcome to Theory of Computation. This is lecture number 36. As you know, we've been studying complexity theory. As I told you before, complexity theory is about resource-bounded computation. We've been studying the classes P and NP, and we've looked at the theory of NP completeness in reasonable detail. We've looked at a lot of NP complete problems, and we have also talked a lot about the celebrated P versus NP question. If you think about it, what we are doing is studying computation from point of view of a resource. And here, the major resource that we look at is time. What we want to do is we want to figure out how much time will be required to solve a given computational problems. And we divide these computational problems into computational complexity classes such as P and NP, in order to classify them according to how much time would be required to solve these problems. Well, now if you think about it, time is not the only resource that is required to perform a computation. If you have done computations by hand, you realize that it's not only time, but sometimes also the amount of paper that you use that is of consideration. Similarly, if you have ever owned a computer, you'd realize that memory is something which is very important component of the computer. Everyone wants to buy a computer which has a large memory, because computers, in order to solve problems, use memory or space. So it is natural to study computational problem from the point of view of this resource. And this is going to be the subject of space complexity. So now what we will do is we will start studying computational problems from a space complexity point of view. The kind of questions that we would ask would be very similar to the questions that we have asked before, except for now the emphasis is not going to be on time, but on the space required to solve a computational problem. We would also define complexity classes, and these would be space complexity classes as compared to time complexity classes. So, for example, we'll define the space analog of the class P, which we would call P space, and similarly we will define the space analog of the class NP, which would be called NP space. So, the outline of the next few lectures is as follows. What we want to do is we want to study the subject of space complexity. We start by looking at what deterministic space complexity is, and then we would look at what non-deterministic space complexity is. After that, we would see a few examples of space-efficient Turing machines, or rather, we would look at Turing machines and we would analyze how much space do these Turing machines require. Then we would look at an extremely important problem in space complexity theory called the reachability problem. And after that, we would look at Savage's theorem, which is an extremely celebrated theorem because it solves the P versus NP, the space complexity analog of the P versus NP problem. In order to study space complexity, we will have to first define how much space is needed or how much space is used by a Turing machine when it performs a computation. What we want to do is measure that how much space is used by a computation. And for that, what we will do is we will take our usual model of a Turing machine and change it slightly so that it's going to be very easy for us to measure how much space was used by a Turing machine to perform a computation. Since we are studying space complexity, the amount of space or memory that is required to solve a computational problem, we will be using the following very convenient model which allows us to study space complexity. Let us consider a Turing machine M which has the following components. So this Turing machine M is just like our previous Turing machine. We put input on its input tape and we turn the machine on, and it moves from one state to another and that is dictated by its program or its transition function. but we make slight changes in this model, and this would allow us to measure space very precisely. This machine will have an input tape that is read-only, and the input is going to be enclosed in hash symbols. So in order to give input to this Turing machine, you put it on the input tape, and the first symbol is hash, and then the hash sign, and then you write down the input, and then you end it with another hash sign. So, and this tape is a read-only tape for the Turing machine. The second component in this Turing machine is it has a work tape that is initially all blank. The third most important part of this Turing machine is that this machine is not allowed to write a blank symbol on the work tape. So here is a picture of this Turing machine. As you can see, this Turing machine has two tapes. The first one is an input tape, and it's been given an input, and the input is enclosed in hash symbols. The other is a work tape. It's implicitly understood that this machine is not allowed to write the blank symbol on the work tape. Well, what happens if I turn such a Turing machine on and let a computation happen and look at it when it eventually halts? Well, I can observe at the end of the computation how many non-blank symbols are written on the work tape. Here is a hypothetical picture of the machine after this machine has halted. As you can see, the input is unchanged because the input tape is a read-only tape. However, the work tape has symbols written on it, and as you can see, they're all consecutive symbols followed by blanks. Since the machine was not allowed to write a blank symbol, we know that this machine never crossed to the right of the rightmost non-blank symbols. So if at the end of the computation we just look at the number of non-blank symbols on the work tape, that would be the amount of space used by this Turing machine. So the space used by a Turing machine on input X is the number of non-blank symbols on the work tape at the end of the computation. Of course, here, since we are studying space complexity and not computability theory, we would only be dealing with Turing machines that halt on all possible inputs. So all these machines are deciders, and we would implicitly assume that from now on that all our Turing machines halt on all possible inputs. Therefore, it makes sense to talk about looking at the work tape at the end of a computation. I give the machine an input X, I run the Turing machine, it eventually halts, and then I go and count the non-blank symbol on the work tape, and that is defined to be the space used by Turing machine on input X. Let us note a few things in this model. The first thing to note is that we do not count the input as space used by the Turing machine. So the space used by Turing machines does not include the input. We give the input for free to the Turing machine, but when it writes a symbol, it writes it on the work tape. That counts as space used by the Turing machine, not the input. The second point to notice is that the machine is allowed to read the input again and again. So this means the machine can go back and forth over the input and read it again and again. However, since the machine is not allowed to write over the input, it's a read-only tape, therefore it cannot use that part of the input tape or the input tape to store any intermediate results. The reason for only counting the space used by the machine on the work tape is, we would see later, that this would allow us to define meaningful complexity classes which require sublinear space. This comment will become more clear as we go through these lectures on space complexity. A good realistic machine to keep in mind is a computer which has a CD-ROM attached to it. The input to the computer is provided on the CD-ROM, which is read-only memory. And we are interested in figuring out how much memory of the computer would be required to perform a computation. So the input does not count as memory used by the computer. You can imagine a CD-ROM spinning in your computer. and so the computer can read that CD-ROM over and over again, and because the input is given to it on that, and that doesn't count as memory used by the computer. The memory that is used by the computer is actually the one that it uses in its RAM or on its hard drives. So this is the model that we are going to look at. This is the definition of space used by a Turing machine. And if you think about it, this is a very, very good definition, because it will allow us to answer very interesting questions. For example, you may want to make a very simple and a small device, say, which reads CD-ROMs and renders those pictures on the screen. And you would want this computer to work on very, very limited amount of memory. Of course, you're not going to count the CD-ROM as the memory that you put in this computer. So this is the model of space complexity that we will follow. Now, let's start with some definitions. Suppose we have a Turing machine M that halts on all inputs. We say that M runs in space Sn if for all inputs of length n, the machine uses at most Sn space. You are used to of these kind of definitions by now. We define what does it mean for a machine to take time Tn. We say that a machine takes time Tn if for all inputs of length n, the machine is guaranteed to halt in at most Tn steps. Similarly, we define Sn to be, we say that a machine takes space Sn if on all inputs of length n, the machine only uses space Sn. Once again, you will notice that this definition is capturing worst case space complexity. So what we do is we look at all possible inputs of length n, and we note what was the maximum amount of space that was used by this Turing machine on these inputs. Out of all these inputs, the maximum is called S of n, and then we say this machine takes space S of n. Now let us start by looking at a few concrete examples. Let's look at a language which you know is a computational problem, and let us design algorithms which are equivalent to Turing machines for this computational problem or language, and see how much space do they require. This would give us some feel about space complexity and what does it mean when we talk about, when we say that this machine takes space n, or this machine takes space n squared, and so on. So let's look at a concrete example. Let us consider the language L, which is the set of all x over 0, 1 star, where x is equal to its own reversal. This is the set of all palindromes over 0, 1. We would look at two Turing machines that accept this language and see how much space they require. So you have solved the palindromes problem many times as an example in this course. So by now you should know what the language palindromes is. It's the set of all strings such that when you reverse them, you get the same string back. The other thing is it should be very easy for you to design a Turing machine which accepts this language of palindromes. Well, let's look at the first machine. Of course, we have looked at this kind of machine before. Let's describe a Turing machine M1 that accepts this language by the following high-level description. This machine copies the input to its work tape, then it moves one of its heads to the left and the other one to the rightmost character of the copy of the input. So what this machine does is it moves back its head that's reading the input tape all the way to the left, and it moves the head that's on the work tape all the way to the right. Now, by moving one of its head from left to right and the other one from right to left, it checks if all these characters match. So one of the heads is at the beginning of the input and the other one is at the end of the input, which is copied here. And it starts matching the characters one by one, moving the head, this head from left to right and this one from right to left. This is a Turing machine that you have already studied in detail. If all these characters match, the machine accepts the input, otherwise it rejects. So this was a high-level description of a Turing machine, and you are by now experts in converting these high-level descriptions into actual definitions of Turing machines. But what we want to do is we want to ask ourselves, how much space did this Turing machine require on an input of length n? Well, it's not hard to see that the space required by M1 is linear. All this Turing machine does is copies the input to its work tape. So the amount of work tape used is only as long as the input. So if the input is of length n, then this machine will copy the input on its work tape, and so it would only require linear amount of space. The interesting question is, can we accept this language in less space? So here what we have is an algorithm or a Turing machine, and now we are studying this question from a space complexity point of view. We said that this algorithm requires space order n, and now we can ask for a more space-efficient algorithm for the same problem. So the interesting question is it possible to accept this language in space little o of n? So can we design a clever way of recognizing palindromes without using linear space? We want to use now sublinear space. Now we want to save space. So how about looking at the following machine? You remember the first machine that we looked at, which was a single-tape Turing machine which recognized palindromes or palindrome-like languages. This machine worked very simply. It crossed off the first character, remembered it in its state, went to the last character and matched it and crossed it off, and then came back to the second non-crossed character, remembered it, went back to the second last character and matched it, and so on. So it sort of moved like this, matching characters, and this was a order n squared. This was a Turing machine that ran in time order n squared, Let's look at how much memory does this, or how much space does this Turing machine take. So let's first give a precise definition of this Turing machine. We read the first character and put a dash on it. We match it with the last character which does not have a cross on it and cross it. If all characters have a dash and get matched, then we accept, otherwise we reject. Here is a picture of how this machine works. So as you can see, this machine has been given an input, and what we have shown is how it has done its work and at the end accepted its input. So the question is, how much space does this computation take? If you remember our model, in our model we said that the input tape was read-only. Therefore, we are not allowed to write anything on the input tape. So we are not allowed to write a cross or a dash over the input. So the way we have described this Turing machine, this cannot fit into our model that we said we will use to study space complexity. But that's really no problem. What we can do is, the only problem with this plan is that our input tape is read-only. However, our work tape is read-write tape. So what we can do is we can copy all the input to the work tape and then carry out this plan on the work tape. And then we can ask the question, well, now how much space does this Turing machine take? So in order for us to make a Turing machine which is according to our model, we must copy the contents of the input tape to the work tape. This would give a machine that takes space n at least. So since we are copying the whole input from the input tape to the work tape, that already requires space n, and therefore this cannot be a sublinear space algorithm. And the question is, can we do better? Can we do better than space n? So at least this naive idea doesn't seem to work. But if you think about it, it almost worked. The problem was that we were not allowed to cross off things on the input tape. So can we use a clever idea and use a little bit of the work tape and zigzag through the input tape without putting any symbols there? Well, the answer to this question is yes. Let us describe this new Turing machine that I'm calling M2 that accepts the same language. The machine writes 1 on its work tape. We call this the counter. So this machine uses the work tape as a counter. And we'll see that this machine may require one more counter. It's not going to be very difficult, but let's first understand this Turing machine from an algorithmic point of view. So we have a counter in which we put 1. It matches the first symbol with the last symbol. In general, it has I written on the counter. It matches the ith symbol with the ith last symbol. Well, so this Turing machine has a counter which it keeps on its work tape, and suppose the counter has I written on it, then what it does is it starts from the start of the input tape and goes I steps further to locate the ith character. It remembers that. Then it moves the head all the way to the end of the input, and then it moves backward I characters and matches it with the character that it read before. So it only uses a counter on its work tape. Well, how can it move I characters? How can a Turing machine move I characters and keep track of it? The answer is it can do that very easily by keeping another counter. In order to match the ith symbol, the machine can use another counter that starts at I and decrements every time the machine moves its head on the read-only tape forward. Similarly, to get to the ith last character, we can use another counter. Thus, if we think about this machine, this Turing machine only uses 3 counters. So it can have 3 work tapes, or it can put 3 counters on its work tape. And then it does not write anything on the input tape. It just scans it and keeps scanning it. First matches the first character with the last character, then matches the second character with the second last character, then matches the third character with the third last character, and so on and so forth. And in order to do so, this machine requires at most 3 counters on its work tape. So the question is, how much space do these counters take? Each counter needs to store a number in binary. This number will reach the maximum value of n if the input has length n. So if you give it input of length n, this counter, once it reaches n, all of the input has been matched and the machine can halt. Now, we recall that to represent n in binary, we don't need n bits, we just need log to the base 2 of n bits. Thus, this machine will require only order log n space. So, this machine does not now require space n, but only order log n space. This is a real improvement over the previous machine M1 in terms of space. Remember, the previous machine M1 that we made required linear space, and this machine requires logarithmic space. Well, let me just say something which is extremely trivial, but just to drive this point home. Suppose that you have a CD-ROM on which somebody has written a string and you want to find out whether it is a palindrome or not. Or let's say that suppose you have a DVD and somebody has written a string on it and you want to find out whether it's a palindrome. Now, a DVD can have gigabytes of memory. But this algorithm only requires log of a gigabyte of memory, or 3 times that much. So this algorithm requires just a few hundred bytes, or in fact even much less than that, less than 100 bits, to tell you whether the string that was stored in this DVD is a palindrome or not. So this algorithm does require extremely tiny amount of memory. On the other hand, the first algorithm that was copying the whole DVD onto its RAM and then matching it was extremely wasteful in terms of space. So, space-efficient computations can be extremely useful, and we use them several in several places in computer science. In fact, there are lots of applications where the algorithms that we know require a large amount of space, especially if you have done compiler optimization. You know that optimizing compilers take a huge amount of space, and there it is a challenge for computer scientists to come up with ingenious methods which save space. And that's the whole motivation of studying space complexity. A few points to remember that are made clear by this example are that if you are claiming that you have sublinear space Turing machine, then make sure that you're not overwriting the input or using that space. So if you've ever come up with an algorithm or with a Turing machine and you're going to claim that this Turing machine uses sublinear space, then you must make sure that you're not overwriting the input. That is not allowed, because that would be counted as space used by your algorithm. So for sublinear space algorithms, it's imperative that you must make sure that your algorithm does not overwrite the input or use that memory at all. The second thing that is made clear is the machine M1 takes order n time and order n space. On the other hand, the machine M2 takes order n squared time and log base 2 of n space, order log n space. So M1 is better in terms of time than M2, but M2 is better in terms of space. And this is quite typical. Typically, what happens in a problem is you have some sort of a space-time trade-off. If you try to save space, you end up spending more time. If you try to save time, you end up using more space. This is called a space-time trade-off. So if somebody claims that they have a better algorithm, perhaps a better way to really analyze the algorithm is to compute how much time does it take and to compute how much space does it take. And then once you know both of these quantities, you can decide whether this algorithm is efficient or whether this algorithm will do the job for you. Let me give you a concrete example. For example, you've heard of two algorithms for sorting. One of them is called merge sort and the other one is called quick sort. Now, as you know, sorting is extremely serious business in computer science. It's a classical problem, and any algorithms, and there are lots of competing algorithms, many ideas. People have thought about sorting for a long time. Don Knuth has written a whole volume on sorting and searching. Sorting is an extremely important problem. Therefore, it's no surprise that sorting algorithms have been analyzed very, very precisely. Well, let me tell you about two algorithms which have been analyzed extremely precisely, and that would tell you the difference between these two algorithms. One of the algorithms is called quick sort and the other algorithm is called merge sort. Let's just stick to average case analysis. You must know that the average case analysis for both these algorithms tells us that both these algorithms take order n log n time. On the other hand, when you look at the space required by these two algorithms, you realize that merge sort takes 2 times n cells space. So if you give it a list of n items, it needs the same amount of memory in order to sort those numbers. On the other hand, quick sort does not require an additional array in order to sort these numbers, but only requires to put some elements on the stack, and that stack can go up to depth of log n if you implement quick sort properly. Thus, if you are looking given that the time required by these two algorithms is neck to neck, if you look at it from the space requirements of these two algorithms, quick sort is clearly a much, much better algorithm if you're only considering average case analysis. Of course, if you're looking for worst case analysis, then merge sort becomes a better algorithm. In fact, space complexity is becoming extremely important, and space is becoming extremely important in computers because what happens is algorithms that require a lot of space end up also requiring a lot of time. And let me explain why that happens. See, in a real computer system, you do not have just memory or space, but on the other hand, you have what is called memory hierarchy. You have registers, then you have local cache that you have on chip, then you have the RAM on the computer, and then you can make virtual memory on your hard drive and so on and so forth. And to access different kinds of memory requires different amount of time. And you have few registers, and then you have a little more cache, and then a lot of RAM and huge amounts of disk space on your computer. Now, if your program is requiring very little space, then perhaps the entire requirements can be fulfilled by the cache. And cache is very quick to access. The access time for cache is very fast, and therefore these algorithms actually end up running practically faster than algorithms which are requiring huge space, because they end up storing things on the disk and the access time is very slow. And therefore, space complexity is an extremely important subject, and space is an extremely important resource in computer science, which we are going to study very thoroughly. Now let us talk about non-deterministic space complexity. Now suppose M is a non-deterministic Turing machine. Suppose that all branches of M halt on all possible inputs. And this is going to be the assumption that we'll make on all non-deterministic Turing machines as long as we are studying space complexity, that they halt, and all branches of these non-deterministic Turing machines halt. We define the space complexity Fn to be the maximum number of tape cells that M scans on any branch of its computation for any input of length n. So the space complexity is now once again for a non-deterministic Turing machine taken over as the maximum over all inputs of length n and over all possible branches on those inputs. Non-deterministic space, just like non-deterministic time, is a useful mathematical construct. It does not correspond to any realistic model of computation. So, you remember then when we started studying non-deterministic Turing machine, we defined the notion of non-deterministic time. Well, we said that non-deterministic time was just a mathematical construction. It was just an abstract idea, and it had nothing to do with machines that you can build. You cannot build non-deterministic Turing machines, and therefore non-deterministic time doesn't really have any bearing on real models. On the other hand, it's an extremely important and useful mathematical construct which allows us to study complexity theory. And it proved to be extremely important because non-deterministic time allowed us to identify NP-complete problems, and that was the utility of it. The notion of non-deterministic time allowed us to define this beautiful class that we call NP. Similarly, non-deterministic space is just a mathematical construct. Well, it's a mathematical construct, and it is going to be also extremely useful when we study space complexity. Now let's take a function from the integers to integers, and what we can do is we can define space complexity classes. So space Fn is going to be the set of all languages L such that L is accepted by an order Fn space Turing machine. Similarly, we will define n space of Fn to be the set of all languages L such that L is accepted by an order Fn space non-deterministic Turing machine. So, once again, these are normal complexity classes we define. We take a function f of n and we say, well, the set of all problems that I can solve in space f of n, I'll call that d space of f of n, and the set of all problems that I can non-deterministically solve in space f of n, I'll call it n space of f of n. Let us consider some facts which make space complexity very different from time complexity. A sublinear time algorithm cannot completely read its input. So if I tell you that I have an algorithm which requires order square root of n steps to solve a problem, or on input of length n, it takes order square root of n steps, well, then you can be sure that for large n, this Turing machine does not read its entire input, because if it starts from the first symbol and tries to read all the way till the end, that's n steps, and since it takes square root of n steps, therefore it must stop reading before it reaches the end of the input. So if we define sublinear time complexity classes, they aren't that interesting, because these are problems that where the answer doesn't even depend on all possible input bits or all possible input symbols of the input. However, sublinear time space complexity classes are extremely meaningful, as we'll see. And it is extremely meaningful to talk about sublinear time space complexity classes. Let us now talk about a concrete problem, an NP-complete problem. You remember the question of satisfiability. You're given a Boolean formula phi, and you're asked if there is a satisfying assignment which makes for this formula, or is there an assignment which makes of the variables which makes this formula true. That's the satisfiability question. We studied this problem in great detail. It was a central problem in the theory of NP completeness, and we proved that this problem is indeed NP complete. Well, let's now look at this problem from a space complexity point of view, and let's ask ourselves how much space is required to solve this question. Let's first define a proper version of this problem, and then look at a Turing machine on an algorithm that solves this problem and compute how much space does it require. We studied CNF satisfiability. Let us see if we can come up with a space-efficient algorithm for this particular problem. Let's say we're given a Boolean formula phi on n variables in conjunctive normal form. So you remember what conjunctive normal form is. You're given clauses, and the question is there an assignment which satisfies each clause? Let x1, x2 all the way up to xn be the Boolean variable that appear in this formula phi, and let c1, c2 all the way up to cm be the clauses in this formula phi. Now the question is, does there exist a satisfying assignment? Does there exist assignment to the variables which makes all these clauses true? And to make one clause true, we must make at least one literal in every clause true, in that clause true. And what we have to do is make all the clauses true. So we're looking for a satisfying assignment. Now we are not looking for a time-efficient algorithm. We suspect that that may not be possible because the problem is NP-complete, and the theory of NP-completeness tells us that it would be highly unlikely that the problem can be solved in polynomial time. But the question is, how much space is required to solve this problem? Can we solve it in reasonable amount of space? So let us look at the following algorithm. What we're doing is we're considering an algorithm or a Turing machine. What we will do is we will go through all possible assignments of x1, x2 up to xn, and for each assignment we'll check if all the clauses are made true. If they are, we will accept, otherwise we would reject. What we will now note is that this idea can be implemented in linear space. So this is the most trivial and simplest algorithm that you can solve, that you can come up with to solve this problem, satisfiability. If somebody is asking you if phi is satisfiable, go through all possible assignments of the variables and check if any of those assignments satisfies all the clauses. Well, the major point is when you go through assignments for each variable x1 up to xn, the assignment can be either true or false. And there are 2 to the n possible assignments. That's many assignments. But what you need to do is just store only one of them at a given point. So for example, suppose you start with assignment 0, 0, 0, 0, 0. all variables assigned 0, then you can store that and check if this assignment makes clause 1 true, clause 2 true, and you can do that by scanning the input and reading what literals appear in clause 1. And what are the values of those literals? You can go back to the work tape and check. Once you're done with the first assignment, you can move on to the second assignment and reuse the same space. In fact, all you'll have to do is, if you have n variables and you start from 0, 0, 0, 0, 0, and you read them in binary and keep adding 1 to it, you'll keep getting the next assignment. And then all you have to do is go and check whether this assignment makes all the clauses true. And for that, what you need to do is only scan the work tape and do not write anything. And so this whole idea, by reusing space, can be implemented in linear space, in space which is order n. Thus, what is happening is, although we're taking exponential time, we are reusing the same space over and over again. Thus, the space requirement of this algorithm is linear. On the other hand, the time requirement of this algorithm is exponential. So, what we realize is there is an NP-complete problem that can be solved in linear space. Each assignment of the variables can be stored in n bits. To make sure that a clause is made true, we just have to read the clause and check if one of its literal has been made true. And both these things can be done in an extremely space-efficient manner. What we have just discussed now is that satisfiability can be solved in linear space. So we have the following theorem. Satisfiability is in space n. On the other hand, we know that satisfiability is NP-complete. Thus, this leads us to the conjecture that P is not contained in space n. But this is, once again, only a conjecture. So, what we suspect is that if a problem requires linear space to solve, it may not be necessarily true that we can solve this problem in polynomial time. Thus, and the reason for that is, as you see in this problem, is space can be reused over and over again. In this case, the space to store the values of x1 up to xn is used exponentially many times. And we suspect that there are problems where this inherent property can be used. However, this is once again just in conjecture. No one knows for sure. Now let us look at a non-deterministic linear space machine. Let us consider the following language, the emptiness language for NFAs. So now what we're doing is looking at a new language, which is the emptiness language of NFAs. In this language consists of a set of all encodings of NFAs A, such that the language of A is empty. We will devise a non-deterministic linear space algorithm that decides the complement of this language. So we will devise a non-deterministic linear space algorithm which accepts the complement of this language. So this Turing machine will accept encodings of all those NFAs whose language is not empty. So the goal is to devise a Turing machine that accepts all those NFAs whose language is not empty. In other words, we want to come up with an algorithm which will identify, non-deterministic algorithm which will identify all those NFAs whose language is not empty. In order to do this, what we're going to do is we will recall some facts from automata theory. So let us recall the following facts. The first fact is that if a deterministic finite automata has k states and its language is not empty, then this machine must accept a string of length at most k. Suppose that a DFA D has k states and it accepts some input x. If x has length greater than k, then when you run this DFA on the input, then it must repeat at least one state. And now what you can do is you can take that part of the input and chop it off and the new shorter input will also be accepted. And you can continue doing that till the string has length at most k. Thus, every DFA with k state, if its language is non-empty, then it accepts a string of length at most k. Let's now look at the second fact. The second fact says that if A is an NFA with Q states, then there exists a DFA such that the NFA is the same as the language of this DFA D, and the number of states in D is at most 2 to the Q. So this is an algorithm that you learn when you study automata theory, and this is the algorithm that allows you to convert a NFA into a DFA. You use this algorithm in your compiler courses and your automata courses, and you also study the fact that the DFA that you make does not need to have more than 2 to the number of states in the NFA. So the blow up in the number of states when you go from NFA to DFA is at most exponential. Well, if we put these two facts together, we obtain the following fact. As a consequence, we get that if A is an NFA with Q states and the language of A is not empty, then A accepts a string of length at most 2 to the Q. And we will use this fact to come up with a non-deterministic Turing machine. Now, let us consider the non-deterministic Turing machine. Recall that we're trying to accept all those NFAs that accept some string. Well, what we can do is on input A, which is a non-deterministic Turing machine, we count Q, the number of states in A, and now we non-deterministically guess an input X of length at most 2 to the Q, and we simulate A on X, and if A accepts X, then we accept, otherwise we reject. So this is a non-deterministic Turing machine, and what it does is it tries to guess the input that would be accepted by the non-deterministic finite automata A. Now, if the language of A is empty, then all branches of the above non-deterministic Turing machine will reject. On the other hand, if the language of A is not empty, then there will be at least one branch that will accept. Thus, the language of this non-deterministic Turing machine is the complement of ENFA. Now, let's see how much space does this non-deterministic Turing machine requires, and it's clear that it requires 2 to the Q space because it guesses the string X, which can have length up to 2 to the Q. However, we notice that in order to simulate an NFA, we do not need to store all of X, but we only need to know its current symbol. Thus, we can reuse space. We can be more space efficient by guessing the symbols of X as we go along and not storing them. So let us consider this new Turing machine. This Turing machine on input A will count the number of states in A, and then it will run a loop in which it will keep guessing a symbol of X, and it will use that symbol to simulate one state of the non-deterministic Turing machine. And if A accepts, then it will accept, otherwise it will reject. So, this is a new non-deterministic Turing machine that accepts the complement of ENFA. And what it is doing is now it is not storing all of the input that it's guessing X, but it guesses it a symbol by symbol, and every time it guesses a new symbol, it takes those steps on the non-deterministic Turing machine, non-deterministic finite automata, and moves its computation one step further. So this machine is once again being space efficient. Let's see how much space does it actually require. Well, this non-deterministic Turing machine will require a counter that can count up to 2 to the Q. And those are the major space requirements of this non-deterministic Turing machine. Such a counter only requires Q bit. Therefore, this whole simulation can be done in non-deterministic linear time. Thus, we have the following theorem. We have shown that the emptiness problem for NFA, the complement of it is in space n. So we've shown that this problem has a space efficient algorithm for it. In the next lecture, we would look at briefly what we have done in this lecture and see what does it teach us, and we'll continue our discussion on space complexity classes, and we'll define the analogs of P and NP in terms of space and prove a wonderful theorem called Savage's theorem. I thank you for your time. I'll see you next time. Thank you and goodbye.